I mentioned in the previous video that when you look at addition reactions of conjugated dienes, you can essentially adjust the product distribution between 1,2 addition and 1,4 addition. And in this section, we're going to explore, the reasons for that. And it's essentially based on both thermodynamic and kinetic control of the particular reaction. And so we see that product distribution varies depending on both temperature and time of a reaction. So let's explore the temperature. Let's look at some data that shows us how this varies with temperature. And we can look at 1,3-butadiene. This is a very common reaction that's been explored. So when I look at the reaction of 1,3-butadiene with HBr, I know that this is going to undergo both a 1,2 and a 1,4 addition. The product of 1,2 addition looks like this, and the product of 1,4 addition looks like this. So we have these two products, 1,2 addition and 1,4 addition, right? And we saw this in the previous section, so 1,2 and 1,4 addition. And when we look at the product distributions of these, we see that when I do this at a very low temperature, so in this particular example, the reaction was run at minus 78 degrees, and I see that the product distribution is 81% and 19%. 81% 1,2 addition, 19% 1,4 addition, right? So we see that at low temperatures, that 1,2 addition is favored over 1,4 addition. And when I heat this up at 45 degrees, now I almost get the complete opposite of product distributions. And as a matter of fact, as you slowly increase, it's been shown that as you slowly increase the temperature, the product distribution switches from, so the 1,2 addition becomes less and less and less, right? So this is kind of an interesting phenomenon. We're going to think about, why this is happening. Now, the second factor is time. And so what we see is that if I take, so this is 3,4-dichloro-1-butene. Essentially, we can think of this as the product of chlorination of 1,3-butadiene, right? So this would be a 1,2 addition product of the 1,3-butadiene. And if I take a sample that has 100% of this product in it, and I simply make up a solution at 25 degrees in the presence of a little bit of zinc chloride, after some time I get my product back, but I also get a product of 1,4 addition, right? And as a matter of fact, so I see this 1,2 and 1,4 addition product. So what's going on here? Well, we could certainly think of that allylic chlorine, right? The chlorine coming off of the allylic carbon, undergoing an SN1 type of mechanism, right, where it comes off, you form the allylic carbocation, and so now it can go back onto that second carbon, or it could go back on. It could go onto the fourth carbon as well. And so you get this product distribution, and that distribution is 30% 1,2 and 70% 1,4, right? We're doing this at room temperature. Now, interestingly enough, if I started with the 1,4, 100% 1,4, and I did the same thing, dissolved it up in solution at 25 degrees with zinc chloride present, I get the same outcome. I get the same distribution that's occurring. Now, notice that product of 1,4 is the greatest amount. Now, we have to be careful of thinking about why it happens to be the most favored product. And when we look closely, we can think about the stability of the alkenes, and we see that the product on the right is the more stable product. Why is that? Well, if you remember, when we talked about alkene stability, we saw that the more substituted the alkene was, the more stable it was. And so this is simply based on substitution. Here I have a disubstituted alkene, and on the right I have a monosubstituted alkene. So that disubstituted alkene is going to be the most favored. So now I have this these two conditions, temperature and time, and I can start to think about what's going on in this reaction. So I can think about a reaction coordinate, right? And think about what's going on in this that would give us these product distributions, and think about why they would change. So if I start with my reactants, 1,3-butadiene and HBr, I know that there's going to be an energy barrier, right, to form the allylic carbocation plus bromide. So I know the allylic carbocation forms, and of course that's going to be the highest energy barrier that I can, because I know that to form a carbocation, still, regardless of it's more stable than a normal carbocation, it still requires the most amount of energy to form that carbocation. And so now I have essentially two paths that I can take for products to form. And so I can think about the first path being 1,2 addition. And so the transition state of this 1,2 addition I'm showing here, and of course the product is going to be here, right? So now at low temperatures, the 1,2 product is always the most favored product at low temperatures. And so what this means is it must mean that the transition state for 1,2 is lower than the transition state for 1,4, right? And so the second pathway we show for that 1,4 transition state has to be at a little bit higher energy, right? And this is why it's not formed at low temperatures. But its product happens to be more stable because it's a disubstituted product. So we see that for 1,2, we say it is kinetically favored. 1,2 is kinetically favored because at low temperatures, short time, you get always, you favor 1,2 addition. And then 1,4 is thermodynamically favored because it's the most stable product. So assuming I have enough energy, right, so higher temperatures or higher reaction conditions, then I'm going to favor the most stable product. In this particular case, it's 1,4. In some cases, that might not be the case. Now, it's easy to understand why at higher temperatures the most stable product is forming, right? Thermodynamics favors the most stable product. But one of the questions is, why is 1,2 addition favored at low temperatures? And in order to think about that, we really have to think about the transition state and what's really happening at that transition state. So if I go back and look at the addition of 1,3-butadiene to HBr, right, I see that here is my transition state, the allylic carbocation, and bromide is coming off, right? So bromide's getting ready to act as a nucleophile and attack that carbocation. And of course, I know that the carbocation, the allylic carbocation, is in resonance. And so I see these two resonance structures of the allylic carbocation. And I notice that one of them is a secondary allylic, and one of them is a primary allylic. And so so we essentially have two possible scenarios in which this transition state depends on. The first is simply proximity, right? As I add H as I add electrons to HBr, the bromide that forms is going to be in very close proximity to the initial carbocation that forms, right? And so we say that that's proximity. Now, the other possibility is it simply happens to be that that's a secondary carbocation. So the allylic carbocation forms and rapidly equilibrates, but the secondary carbocation aspect of it is weighted more heavily than the primary carbocation aspect, and so the bromide attacks that secondary carbocation. So one of the questions is, well, how do we determine which one is which? And there was a group from Case Western in Cleveland, Ohio, that actually studied a reaction where instead of taking 1,3-butadiene, they took 1,3-pentadiene, and they reacted it with deuterium chloride. And so when deuterium chloride reacts, it's going to react with the carbon between C1 and C2 versus the carbon between C3 and C4. And the reason for this is because that forms the most stable allylic carbocation, right? And so here I get the addition to form my allylic carbocation. Of course, I know that that allylic carbocation has a resonance structure, right? And so in this particular case, both of those resonance structures have secondary allylic carbocations. So neither one of them is going to have a weighted resonance, so to speak. And so we think about, how chloride is going to react, and of course it could react at the carbon on the left, or it could react at the carbon on the right. If it reacts with the carbon on the left, we get this product, and if it reacts with the carbon on the right, we get this product. And so we can think about the product distribution. Now, if this transition state is solely based on proximity, then we should see the product on the left, right? Because the chloride is closer to the carbocation on the left, and so we should see more product on the left than we see product on the right. If, however, the transition state is based on a weighted resonance, then for both of these, there is no weighted resonance. Both of them are secondary allylic systems, and therefore we would expect to see a 50-50 mixture. What do we see? We see a 76%, 24% mixture, and therefore this leads us to thinking that it's solely based on proximity and not weighted resonance. And this makes things a lot easier for us, really, in terms of predicting products. So, kinetics, short time, low temperature, we see favors addition based on proximity, right? So this is always going to be 1-to addition. So when we say that if a reaction is favored kinetically, then we're always thinking about 1-to addition. Thermodynamics, on the other hand, long time, higher temperature, and this always favors the more stable product, right? So you have to look at which one of them has the more substituted alkene, and that's going to be the one that favors the product that is favored thermodynamically, right? So let's look at an example here. We have 4-methyl-1,3-butadiene. 4-methyl-1,3-pentadiene, and we react this with HCl. And so you see that in this particular case, the HCl is going to, so the pi bond between the 1,2 is going to add to HCl, not the pi between C3 and C4. And we'll talk about why that is later on. But these are my two products. I get the 1,2 addition and I get the 1,4 addition, right? So here I have 1,2 addition and here I have 1,4 addition. So I know that the product of 1,2 addition is always kinetically favored. And if I were to ask you which one of these products is kinetically favored, which one is thermodynamically favored, you're always going to select the one that is the 1,2 addition as the kinetically favored product. If I asked you, on the other hand, which one is thermodynamically favored, now you have to look at both products. You can't just say 1,4 is favored over 1,2. You simply have to look at which one of them is the most stable alkene. In this particular instance, you see that the alkene from the 1,2 addition is tri-substituted. The alkene from the 1,4 addition is di-substituted. And so the 1,2 addition product is actually more stable than the 1,4. So it also happens to be the thermodynamically favored product as well.